Welcome to the lesson for 5.1 on geometry. Can be found on these pages. And here's your new vocabulary and the reminder to use extra examples in your book. Don't forget to do that as you're working on the problems for this assignment. So let's get into it. 5.1 perpendiculars and bisectors. Here's what we got to start. Well, first of all, what is a perpendicular bisector? Let's define that. So perpendicular bisectors let's just say bisector here. So perpendicular bisector, what's a perpendicular bisector? All it is this. It's a segment, ray, I shouldn't say or quite yet, segment, ray, line, or plane. Perpendicular, I'll use my symbol for that, perpendicular to a segment at its midpoint. So if I were to draw a segment, I'll do that right now, and I would say that I'm going to draw a line. In this case, that's a perpendicular bisector. So to me, I'm going to say halfway is right there. So I'm going to draw a line that cuts that in half. To make it a line, I'll put my arrows there. And I will add in box in the corner, signifying that it is in fact perpendicular to this. And then I will put tick marks here and here, and now that's saying I'm going to give this endpoints as well. I'm going to call this some kind of a random point right there. I'm going to call that point C. I'm going to call this A and B. I'm going to call the spot where to intersect, I'm going to call that point P. So in this picture, this would be true. It would be true that CP, line CP, is a perpendicular bisector of segment AB. So you have to have a segment to start, and then you could have a line like I have here, or a segment, or a ray, or a plane. All those things can be a perpendicular bisector. I'd say lines are most popular and most often used things for perpendicular bisectors, but we could have any one of these four things. So let's look at a couple of theorems here. We're going to make a little table of sorts, just with two spots in it. And I'm going to take what I had over here, take this picture basically, and just kind of copy and paste it. So I'll do that right now. Then again, I'll just draw it, I think. That will give you some time to kind of catch up with me. So this, let's draw essentially the same thing we had here. So I'm just going to redraw that over here. So I'm going to start with a segment. Then I'm going to draw a line that splits that in half. I'll put arrows on that so we know it's a line. And I'm going to draw endpoints in, so I'm going to say that's A and B once again. Put my box in the corner, call this P again, call this point C, and now I'll copy and paste this. And so please do the same thing. Pause the video for a moment if you need to, and then just take a moment to catch up with me there. So take the picture, copy it over here. We are going to get rid of this though, so I don't want that in this picture. I don't want the 90-degree box in the corner for this picture. Everything else, so I do want this one though. I'm going to add some things in, or I'm going to add one more thing in here. So I'm going to put in one more set of segments from there to there. I'm going to call this point where they intersect, I'm going to call that D. I still want to call this point P up here, and then this point is going to be called D right here. So that's point D. And I'm also going to say that on these pictures this was true, that this was congruent to this. And in this picture, same thing, and then this one, AD is also congruent to BD. And so this first part here, this is the perpendicular bisector theorem. Our first theorem for chapter 5. It is theorem 5.1. Over here is the reverse of that. It's the converse of the perpendicular bisector theorem. And what do you know? It's theorem 5.2. Alright, so second theorem in our chapter. The perpendicular bisector's theorem says this: it is now time to get out your different color. So I'm going to use orange for that. If you want full credit on the notes here, you must use a different color at this point. Not like that. There we go again. Okay. So I'm going to connect A to C and B to C with my different color, and I'm going to say that this is true. So if I had a picture that looked like what was in black to start, I could also say that this is true. That if PC was a perpendicular bisector of AB, that means if I connect A to C and I connect B to C, that they're also going to be the same. That I hope makes intuitive sense. If the line was not perpendicular to it, then it would have a bit of a slant to it. BC would be shorter than AC if it was tilting this way, but it's halfway in between. It's perfectly straight up and down perpendicular to this in this case. So this and this segment are going to be the same. So let's write that down here, that this is in fact true. So you put this in your different color as well, that CA equals CB. So we're starting with what's in black. That's true to start, and then we can prove what's in orange. Over here, we're starting with what's in black, so we've basically got the same sort of idea here as we do over here, just connecting a point now D instead of C. So I could connect AC to BC, and I could basically say the same thing as I am connecting A to D and B to D. But what's true if this is true? If there's 2 points, you have this line. We don't know that it's perpendicular right now. That's not in there. We do know it's bisecting segment AB. We also know there's this other point here where these are also equidistant. What's true then? This is also true. So that if that's true, where you have the segment itself cut in half, and then you have two other segments getting connected to the endpoints like this, we know that D is on the perpendicular bisector of segment AB. That is why I could draw the perpendicular box, the 90-degree box in the corner here. Alright, so let's make an example, or look at an example where this is true. So this is all in a different color. If you want full credit, let's check out example 1 here. So this I've already drawn kind of a kite looking shape, and I'm going to add some extra stuff in here too. So all this stuff going in black, this is all here to start. This is all original stuff. So that's going there. And we're also going to have a line, vertical line in this case. And it's going to go, I'm going to say it goes right there. We're not going to show that it touches this point for right now. We're just going to leave it at that. We're going to see if that might be possible to prove. So I'm going to say this is a line. It would continue this way and then You also continue this way and give some labels to your points. We're going to call this C. This is still something I want in black. So these are things to start. So this is C, this is D, this is Q, this is P down here, this is 90 degrees, and let's see what else we got. Yes, this is 7, and this is 7, and this point is going to be point T. So let's write down some things that we can tell, or we can say for sure are true in this picture. So one thing I can see is true in this picture is, I forgot to add one more thing. That's one last thing I believe that I need to add. I can look at this picture and say, well, CQ is clearly the same or congruent to DQ. So I'm going to say CQ is congruent to DQ. If I had to give a reason for that, I would just look at the picture and say that was given to me. That's just right there in the picture. Boom, boom. Those are congruent. What else is true? I can see in the picture that TC is congruent to, well, TC is 7. What else is 7? TD is also 7. So I can say that TC and TD are congruent to each other. That's given. And I can see that PQ, line PQ, is a perpendicular bisector. Of what segment is a perpendicular? What segment is it the perpendicular bisector of? If you look at the picture, I hope that's clear that it's cutting CD in half, and it is perpendicular to it as well. So it's a perpendicular bisector of segment CD. This is also given in the picture. So is there anything else we can look at the picture and say, well, this also has to be true then? Well, let's go back to our two theorems that we just saw, and we notice that if you have a perpendicular bisector and you connect the endpoints to another point on that perpendicular bisector, those also have to be equal to each other or congruent to each other. So I can look at this picture and I notice, hey, PC, PD, based on that theorem right there, they must be congruent to each other as well. So I'm going to take now my different color out. Take out your different color if you want full credit, and let's add that in the picture. We'll put that in our different color. For me, it's orange. So I can now say, looking at that, let's put this in, we'll write this in a different color too, so that I can say that PC is congruent to PD. This is not given to me originally, but based on the theorems that I just learned, I can say this is true by theorem 5.1. Hopefully intuitively that makes sense. You just look at it and they say, yeah, that seems to make sense to me, but based on that theorem we can prove it's actually true. So PC is congruent to PD. And what else could I say? So I notice, oops, don't want to go there yet. I notice that, well, if these things are equidistant, like I have here, BD and AD are the same, then D has to lie on that line. And so if I look here, I see that TC and TD are the same. So this perpendicular bisector line would actually continue up this way. Put this in our different color, and I could add that in and say, hey, T also lies on the perpendicular bisector. So I would say T is on the perpendicular bisector of segment CD. All that going in your different color, pen, colored pencil, whatever you got with you, but not in the same color you're using to do the rest of the note. So T is on the perpendicular bisector of segment CD. That has to be true as well. So that with the colors, that makes it a lot more clear as to what was there to start and what we added. Let's look at a couple other things, and we will call it a good set of notes from there. So let's make this important point. So to find, it's kind of just a standalone point here. To find the distance, from a point to a line, we're going to always use a perpendicular segment. And I think I'll quickly just illustrate what I mean by that. So let's say we have a line. I'll just make a horizontal line for now. It doesn't have to be a horizontal line. And then we have some point off here. What's the distance? Is it a line that looks like, could it be a line that looks like this? You drew that in, is that the distance? No, because it's not what to this line? It's not perpendicular to this line. This is not the fastest way to get from the point to the line, in other words. But if you were to draw a perpendicular segment to that, there's a perpendicular segment to that. So this right here is perpendicular to there. And so I'm going to make a little notation here and say this is, let's do this in a different color here. So this one, it's not the distance, because B/C is shorthand for that, because it's not perpendicular. But this one, this segment is the distance. So this one is a distance because it is perpendicular. So let's make that distinction right here. So this segment, not the distance, because it's not perpendicular. I could have any segment this way, this way. These all would not be the distance between the point and the line because they're not perpendicular. But if it is perpendicular, then it is the distance. That's what we would consider the actual distance between that point and the segment. And then we're going to draw in one more table here. So let's use vertical and horizontal lines here. So draw that in, something like that. And then two more theorems to go here. So we're going to draw in something to that effect. And I want this to be perfectly mirrored over going down this way. So I believe I have a tool that will allow me to do that. So I'm going to take this and I want to mirror that. So I'm going to go in the y-axis. So I'll just have to move, oh, not like that. I'll undo that. Let's see. I wanted to not just mirror it. I didn't want to mirror it. I didn't want to flip it. That was my problem. So mirror it in the x-axis. That should do it. There we go. And then I'm going to move this down here. That's what I want. Okay, and this coming down here. So do the same thing with yours, and now I've got this this angle that's perfectly reflected this way. So now I can draw. I'm going to draw in a horizontal part to this right here. Okay, and so over on the other side, I'm going to take this, I'll make a duplicate of that, I'm going to move it over here. So you'll need to draw a second one here, but on this other one, take this part right here and get rid of that. So I don't want this in this one. Just want the angle itself over there. Alright, and so from here, I'm going to say some things are true. So still using my original color, I'm going to say that this angle and that angle are congruent. And I'm going to call this point A. And I'm going to pick a point out here, kind of at random. Call that point D. And then from there, I'm going to get out my different color again. I'm going to do, I'll go down this way first. Okay, and I'm just going to take this and mirror it as before in the x-axis. Alright. And so if I draw something like this, where I'm going to give these points labels to, this is going to be point B, and this is going to be point C. If I have something like this, and I had this drawn in like this, where this is true, I should actually say the stuff in black is true to start, and then AD is the angle bisector now of angle BAC. If that's true, where AD is angle bisector, that means that the distance from B to D would have to be the same as the distance from C to D. And to designate that it's actually a distance, remember we have to say the distance is the perpendicular segment here. So to make sure that that is clear, I have to say that that's perpendicular to that, and I have to say that's perpendicular to that. So in other words, the distance from D to ray AB is the same as the distance from D to ray AC if AD is the angle bisector for this. Because we're talking about angle bisectors, they gave it a really good name. Here was the perpendicular bisector theorem. Now we have the angle bisector theorem. So this is the angle bisector theorem. This is theorem 5.3. And so it says if the stuff in black is true, then this, what I have in orange, put this in a different color on yours, this has to be true as well, that dB equals dC. And notice again, dB is perpendicular. It's the perpendicular segment. It's the distance from D to this ray. It's the distance from D to the other ray, forming the angle. In this other one, it's again the converse. So this is the converse of the angle bisector theorem. This is 5.4. And so what I have going on here, this I'll put in orange, I'm going to say that I start with this, and I feel like I'm not quite ready for that yet. So I'm going to pick a point at random out here, and I'm going to say that when it's not totally at random, you'll notice it looks like it lies on the angle bisector. And so I'm going to say this is point D, and I'm also going to draw in some segments here. So I'm going to put that, I'm going to go this way first with that, like before. Now I'll take that and mirror it once again. So you're doing the same thing with yours. Mirroring the x-axis. And just need to make some minor adjustments here. Let's redraw this again. Okay. Hey, did not do that. Didn't lift my pen there. There it goes again. We're going to pretend like that never happened. Still doing it. So I'm just going to go like that. And I'm making this perpendicular here as best I can. And so I'm going to label that like that. Make sure this is actually 90 degrees. If you were to measure it with a protractor, it should actually be 90 degrees. And saying the same thing here, that this is actually 90 degrees as well. Make it look like it. It shouldn't be totally skewed. And we're going to say that this is now true to start. So notice it's the reverse of what we had over here. So I'm starting with the orange stuff. This is true to start. And what can I now say has to be true based on what I have there? The theorem tells me that this actually has to be true. So that if I draw in the angle bisector, that it actually goes through point D, this point that's equidistant from both rays of the angle. So this right here, I can draw in angle there. That's in a different color. That's in my other color. Here we go. So I can say that this and this are actually true. And give my points the same labels as before. So these are still points A, B, C, and D. So what's true here? What are we added in the different color? We are saying that the measure of angle BAD is equal to the measure of angle CAD. In other words, you got a picture like what you have to start with in black. Again, to reiterate the point that had just been made, that's true, this is equidistant to this. If that's true to start, then ray AD has to be the angle bisector for this big angle. The two angles, in other words, have to be equal to each other. So we're going to stop that right there. Hopefully that will help you considerably as you work through some of the problems in this lesson. Remember some of the things here we have to have for equal or for distances from a point to a line. It's got to be that perpendicular segment. A very important point to make there. And don't forget these two theorems as well. So hopefully that helps you. Let's work through now some problems with perpendiculars and bisectors once we get to class. Alright. Have a good one, everybody.